Here we go, chapter 14, some fresh material for the final. If I sound weird, it's because I'm numb from my dentist appointment. The final exam is next week. It should be on Tuesday at 12:30. It's on the calendar. It's also on the syllabus. You can also check the Reedley College website for the final schedule and try to interpret what they mean. I think I interpreted it correctly, but if we show up and there's somebody else here, then I didn't. All right. Radioactivity was discovered a while ago by Antoine-Henri Becquerel, presumably French. The French did a lot of radioactivity stuff for some reason. He hypothesized that the greenish glow of what's called phosphorescence, basically like if you think of those glow-in-the-dark watches, the little watch hands, that's sort of like phosphorescence. I think that might actually be phosphorescence. It's that idea. He hypothesized that it was associated with the emission of X-rays, which we can't see. So that's, not correct. What he did is he exposed some potassium and uranium sulfate crystals to sunlight, basically like that glow-in-the-dark paint. He exposed it to sunlight, and then he put it on a photographic plate that had a piece of paper or something underneath it to block it from absorbing light. And then set that in a room somewhere. And then later picked up the crystals and said, look, the photographic plate has developed. It's been exposed to some sort of light. That means that it must have been from these crystals. They must have absorbed something, and then they released a different thing, and that caused my photographic plate to develop. What is radioactivity? It's the emission of tiny energetic particles. We've got a nice little old-style graphic of that here. And this is emitted by the nuclei, the nucleus, plural, of certain unstable atoms. So some atoms, for whatever reason, just like us, are unstable. And they might occasionally emit particles, and then they settle down for a while. You maybe have experienced this. I certainly have. You get a lot of feelings or emotions, and then you let them out, and then you settle down. And that's the same thing that nuclei are doing. And so these atoms, these unstable atoms, we call radioactive. Some of these particles can pass through matter. So like they could come through the walls, just like a Jedi. Back to our story. Becquerel believed that his hypothesis about X-rays was correct, and that phosphorescence, that glow-in-the-dark paint thing, and X-rays like you get at the dentist were linked. Presented them to the French Academy of Sciences, but retracted the results because he had the crystals on the photographic plate in the dark. They hadn't been exposed to sunlight, and so they couldn't have been emitting that glow-in-the-dark light, and it still developed the photographic plate. And so he realized the crystals were emitting something. He called them uranic rays. We now call that, or we'd classify that within radioactivity. Uranic rays because there was uranium involved. So that potassium uranyl sulfate crystal thing that he was doing. That's just kind of like a little bit of history for you. Later on, Marie Curie, also French, what are the French doing with radioactivity, was one of the first women in France to pursue doctoral work, so going for a PhD. She discovered a whopping 2 new elements while she was searching for substances that emitted uranic rays, aka were radioactive. The first was named polonium, which we have on the periodic table, PO. And the second one was radium, Ra, named for its high level of radioactivity. And Curie is the one that we credit with changing the name of uranic rays to what we now call them, radioactivity. In 1903, the Nobel Prize went to Becquerel and the Curies, Marie and Pierre, for their discovery of radioactivity in 1911, Marie Curie was awarded the Nobel Prize in Chemistry for the discovery of polonium and radium, making her the only person to receive 2 Nobel Prizes in different science fields. There's other people that have won 2, but they were in the same science field, I think, or in one science and not science. Regardless, impressive. In this picture, I think that's, well, it's definitely Marie on the right, and I think it's Pierre in the middle and Becquerel on the left. We're sort of not to the important stuff yet. So like if you're worried about, oh, I'm not going to remember all these details, that's fine. It's not that important. To me, that you know the history, just nice to hear it. More on our story. Curie focused on discovering different radioactive elements. Other people, like Ernest Rutherford, if you add an eum, that's an element, focused on characterizing radioactivity. So what does it do? How is it produced? What sort of energy does it have? What can we do with it? All sorts of things like that, instead of just looking for where can we make more of it. And from Rutherford's work and the work of others, we know that the nuclei, the protons and the neutrons part in the center, of radioactive elements are unstable and spontaneously just by themselves without any outside stimulus decompose. They break down into other things. And the way that they break down or decompose is by emitting small pieces of themselves to gain stability. And there's a few types of radioactive emissions that we'll cover in this class. These are all ones that you should know. We've got alpha, beta, gamma, and positron emission. There might be one more, but definitely those 4. Those are the 4 most important ones. And the little symbols here are the Greek letters, alpha, beta, and gamma. Questions so far? I alluded that we were going to be covering some stuff that we haven't thought about probably in months. Here it is, nuclear symbols. So we can represent a particular isotope one particular configuration of an element, a certain number of protons, a certain number of neutrons, a certain number of electrons. We can designate that using this type of a symbol, A over Z X, where X is the chemical symbol from the periodic table. A is our mass number. The mass number is the protons plus the neutrons. And our atomic number Z is what makes it that element. That's the number of protons. That mass number is always going to be the bigger number compared to Z. Also, symbol-wise, putting A over Z makes sense. At least to me, it comes first. I have lots of experience with coming last, because my first name starts with Z, and elementary school, straight to the back of the line. And you can calculate with these 2 numbers the number of neutrons by subtracting the mass number, since that's protons and neutrons. You can subtract from that the proton part, and what you're left with is the neutrons. So we've got this little formula that you could use. I don't think I'd provide it for you if you need to do an isotope calculation. That will show up because we covered it in some other chapters, so it'll probably show up for those respective chapters. Exam 2, maybe? I don't remember. Most elements have several different isotopes. They can have a lot, even if they just have a couple of primary ones. There's many that can occur. We can refer to a specific isotope of an element as a nuclide. So nuclide here just meaning a specific isotope. Another way that we can represent them is by the element name or symbol followed by the mass number. So let's say sodium has, it probably has a sodium 23. And so we could write it either of those two ways. The 23 is which, the mass number or the atomic number? It's the mass number. It's the mass number because this is the one that we can't know from the name. From the name or the symbol, we can look at the periodic table. Sodium has that 11 in the top right corner. That's its atomic number. The atomic number determines which element it is. We can also represent subatomic particles, so the pieces that we build atoms with which we build atoms, can be represented with nuclear symbols as well. So for the proton, we give this the symbol P. For the neutron, we give it the symbol N. For the electron, surprise, we give it the symbol E. And, perhaps no surprise also, the proton has a mass number of 1 because it has 1 proton. It has 0 neutrons. Also, since it has 1 proton, it has an atomic number of 1. So that's why it's 1 over 1. The neutron has a mass number of 1 because there's 1 neutron, but it has 0 protons, and so for its atomic number, it's got a 0. And then the electron, confusing perhaps with how we've used it, has a negative 1 for its atomic number. Negative 1 proton, negative 1 charge. So that might be a little bit of a weird thing. Questions about any of these rules that you seem to be having a lot of fun listening to? All right, our first type of radioactivity is alpha decay. Big, bad alpha decay. So alpha decay is characterized by the emission of a particle composed of 2 protons and 2 neutrons. Two protons and 2 neutrons is the same as a helium nucleus. Because helium has 2 protons and 2 neutrons, so that's why it has a mass number of 4. It also has 2 protons, that's what makes it helium. And so we'll often represent our alpha particle just as a helium nucleus. It's not the same as a helium atom, because a helium atom also has what? 2 electrons. We don't have 2 electrons here, so that's why it's a nucleus instead of an atom. So this is the first radioactivity that you should know. Expect a question about one of the 4 types of radioactivity on the final. The way that we represent alpha decay, so the emission of an alpha particle, a helium nucleus, is with a nuclear equation. And nuclear equations seem scary because there's a bunch of numbers. All that's going on here is 2 very, very basic algebra equations. And I'll talk about those in a little bit. So a couple of rules. Because we know that mass is neither created nor destroyed, we have to have an equal amount of protons and neutrons on both sides. And so the mass numbers, that's the 238, the 234, the 4, those need to be the same on the left side and the right side. So in this case, 234 is equal to 238 equals 234 plus 4. That works. Easy maths. We also have our atomic number, 92, has to equal the atomic number of the other side to ensure that we have the same number of both protons and neutrons. So 92 equals 90 plus 2. In nuclear reactions, elements are often going to change their identities because they're losing protons, or they're gaining, in some cases, protons by losing neutrons. So here's those equations that I was talking about. And we've got terms for the element, the isotope that broke down, and the isotope that was created. We call them the parent nuclide and the daughter nuclide. Why we don't call it the son nuclide, I don't know, but there's our names. Parent nuclide, daughter nuclide. Questions so far? All right. We want to write some nuclear equations for alpha decay. We can deduce, we can calculate the mass number and the atomic number of the unknown daughter nuclide, that's this XY question mark, because our equation needs to be balanced. So the two equations that we're putting together, we're putting one together for the top numbers, one together for the bottom numbers. I will usually write them out like we see them here. So 232, that's the mass number for our parent nuclide, equals, where the arrow goes, x, that's the mass number for our unknown isotope, plus 4. If we solve for that, subtract 4 from both sides, our mass number is 228, so that's going to go into our top number. To solve for the bottom number, 90, our atomic number for thorium, equals whatever y is going to be, and the 2 that went into helium. So 90 minus 2, y must be equal to 88. And then we would look at our periodic table, find 88, it's Ra, and assemble our numbers. So that's about as intense as the math gets for, I would say, a half to a 2/3 of this chapter. So if you're feeling good, that's great. It'll get more confusing later, so you can save that confusion energy for that time. Let's say that we want to write a nuclear equation for the alpha decay of uranium-238. This problem provides us with a little bit less information, so there's some things that we need to bring to the table to be able to solve this problem. One of the things that we get for free is we're dealing with uranium-238. So we can assemble the way that we write out these isotope things using that information. So we've got that it's uranium, that's going to be our symbol. The 238 is our mass number. In this case, there's a couple of ways that we know that it's our mass number. For one, it's bigger than 118. That's our biggest atomic number, so that number has to go, the 238 has to go on top. Otherwise, we wouldn't be able to get big number over little number. Or we could have just remembered that it's that one. And then the symbol U goes for uranium. We'd find uranium on our periodic table. Look in the top right corner. It's got an atomic number of 92, meaning it has 92 protons. The thing that we need to know, that we need to bring to the table for this equation, is what alpha decay means. So alpha decay means loses a helium nucleus. That helium nucleus is 4/2 he, because it'll never be him. And we also need to know how to write out our decay thing. The parent nuclide, the uranium that we started with, is going to break down into a daughter nuclide and our alpha particle. So we can write in that 4/2 He. And then we've got a couple of boxes to fill in for our symbol. Write a big question mark. We'll call these X and Y. You can call them whatever you'd like. Steve and Bob if you want. Tracking so far? Next thing we do, algebra. We are going to have equal numbers of protons and neutrons on both sides. We can write out equations that make our mass number add up, those are the top numbers, and make our atomic numbers, the bottom numbers, add up. So 238 and 92 are what we're starting with for uranium. I'm going to scooch this 238 equals up. And we're going to have X and Y plus 4 for the top one, plus 2 for the bottom one. You may not even need to use a calculator for this. Question?
So every equation we do for the helium, it's the one we're going to use for each equation?
For every time that we use alpha decay, it's always going to be the 4/2 He, as long as it's alpha decay, because that's the alpha particle. There's other types of decay that'll be different. It won't be the 4/2 He, it'll be something else, and we'll learn those coming up. Other question?
Do we always have to set it up like this? Or this is again just for us to visualize and understand?
You always, for writing, we're asked to write a nuclear equation, so that's what we've got out here in the middle. That will always be the same. It doesn't really matter if you put the alpha particle first or second. You don't have to do these equations. This is just so that you can see where the numbers are coming from. If you can do it in your head and get it right every time, then you're welcome to do that.
It's just the middle part that we're looking for.
Yeah, the middle part is what you'd be asked to identify on an exam. Okay, I'm going to duplicate this. So from our two equations, if we rearrange and solve for those, we get 234 for the X, and the Y is 90. So I'll fill those in. And how do we get the symbol? Yeah, based on the atomic number, so we look up 90 on our periodic table. That's got the symbol TH. So we put TH in, and that would be our nuclear equation. Question?
How did you get the TH?
Got the TH from the periodic table, so you find the box with the 90 in the top right corner, because that's the atomic number. And the number of protons determines which element it is, so those two are linked. That's why we don't have to include it for this U-238 or uranium-238 notation that we had in the problem. Any other questions? We're going to be doing other examples for our other types of decay. All right, so some more information about alpha decay. You can think of, we're going to be using a traffic analogy, sort of, for our vehicles. Alpha decay, or alpha radiation, is our 18-wheeler truck. It's our big rig of radioactivity. It's the most massive particle that's emitted by a radioactive nuclei, at least that we'll cover in this class. it has the highest ionizing power. It hits like a truck, like a big rig truck. It also has the lowest penetrating power. It's going to get stuck in traffic. If you ever see an 18-wheeler truck trying to weave through traffic like they're a motorcycle, call 911. Or just wait for them to hit a bunch of vehicles and then they won't be able to move anymore, right? So that's ionizing power. It's really hard. The ionizing power is the ability to ionize, like knock off electrons or protons or break things up for molecules and atoms, which is damaging. So because it's so big, it's got a lot of mass behind it, it's got a lot of energy that comes with it. So when it runs into something, there's a much higher amount of energy being deposited. That energy that's deposited into the atoms and molecules can cause chunks to break off. It's enough energy that the bonds might break. But again, it doesn't get very far. So kind of the first thing that it runs into, it stops. So that's the penetrating power part. The ability to penetrate or go through matter. So for radiation that's on the outside of our bodies, our skin layer protects us a little bit. Alpha radiation has really low penetrating power. And so like things like a sheet of paper or clothing, or just having some distance and air between us, between that ionizing radiation source, that can be enough to stop an alpha particle. So if you're around an alpha particle source, it's relatively safe as long as you don't get it inside of your body, because the mucous membranes inside your body, not quite as thick as your clothes and your skin. So you've got less protection from them. Our next type of decay / particle number the second. In beta decay, an unstable nucleus emits an electron. So our beta particle is just an electron. And what happens when we emit an electron, part of the reason that we've got this -1 for the atomic number, is a neutron gets turned into a proton. How does it work? I don't know, but you can look it up if you're really curious. But that's how it works, and the math works out for it. So the 1/0n goes to 1/1p plus 0 over -1e. So the 1 and the -1 for the atomic numbers, if you add those up, that equals 0. So the math works out for doing nuclear equations. The tricky part maybe would be remembering that there's a -1 in that atomic number position for our beta particle. An example of this is Ra228. This can turn into, I think this is actinium-228. So its atomic number actually goes up 1 when it undergoes beta decay. All right, let's write a nuclear equation for the beta decay of carbon-14. The gimme here is the carbon-14 part. our symbol for carbon is C. The mass number is 14. And the atomic number from the periodic table is 6. That will go on to produce something plus beta particle. I'll give you some time to work on that since we did an example just a little bit ago. See what you come up with. All right. So some of the information that we need to bring to the table for this type of question is what a beta particle is. Hopefully you wrote it down on the previous slide. There's our beta particle. And then we can set up some equations. You probably don't, hopefully you don't need to do an equation for the top part. It's just going to be the same number. Because 14 equals 14 plus 0. Pretty easy math. You might not even need to do an equation for the bottom. I'll go ahead and do it anyway. So 6 equals something plus negative 1. If we add 1 to both sides, that'll get rid of the negative 1. So it's 7. 7 corresponds to what element? Nitrogen. So we can fill in nitrogen, and there's our nuclear equation. Compared to alpha decay in our traffic analogy, beta decay is the four-door sedan. Could be a two-door sedan. The idea is it's a normal-sized car, an automobile, something that you probably might have driven here. Smaller than alpha particles. Also carries with it less mass than alpha particles. And because of its smaller size, it has lower ionizing power. When it hits something, it has less energy. It's less likely to cause the atoms, the molecules, to break apart. It's the same way as if you were driving on the highway and you had a choice of being hit by a semi-truck or a four-door sedan. Hopefully you would pick the four-door sedan. If you would pick the 18-wheeler truck, we have mental health services available on campus. You can go see them. Question?
On the previous slide, you said 6 plus negative 1 is 7.
So we had a negative 1. I wrote plus negative 1 because I'm pedantic. We add 1 to both sides to get rid of the negative 1. So the 1 plus 6 gives us 7. Another feature of the smaller size is that it's got higher penetrating power. Occasionally you can see people driving on the shoulder maybe of the highway or freeway illegally, and sometimes the wee-woos go on and you feel really good about that. But they have higher penetrating power. There might even be some instances where traffic's merging down, 5 lanes are going down to 1 lane for some reason, and some of the sedans and other vehicles will be going crazy in there. If you get a semi-truck in that same situation, they're just going to be driving really slow and kind of like, all right, guys, just drive around me, I guess. So more likely to get through traffic. So can weave through traffic more easily using that analogy. Compared to being stopped by a sheet of paper or clothing or air, beta particles can be stopped by a sheet of metal or a thick piece of wood. So considerably more protection is needed to stop a beta particle. And that makes it more dangerous if it's outside of the body because it'll probably go through your skin. It'll probably have some opportunity to damage some of your internal organs. But if you were to accidentally ingest a source of beta decay, it's going to do less damage because of that lower ionizing power. Our third particle it's not really a particle. I'll just write number 3. Gamma rays. Gamma rays are a form of electromagnetic radiation. If you remember back to the one slide that we had with the whole electromagnetic spectrum and there was a little tiny cutout of the visible spectrum, gamma rays are like the way high energy side of that electromagnetic spectrum. So they're high energy photons, like really high energy. Since it's just electromagnetic radiation, you can think of it as like super UV light. It doesn't have any charge. It doesn't have any mass. If you're emitting gamma radiation, nothing really changes. It's just emitting energy. However, it usually also goes along with another type of radiation. So this might just be a tag on to another type of radiation. And our symbol is this weird looking Y with a 0 over a 0. Since it goes along with other types of radiation, I don't think we have an example slide for this because it would be like an alpha or beta decay problem. So this is an example of uranium-238 plus helium plus thorium, and there's also some gamma rays coming out of that. So there wouldn't really be anything to solve here for gamma, so expect for a nuclear equation alpha or beta, and also positron that we'll learn about after this. Question?
What's the 2 coefficient?
Just there's 2 equivalents of gamma rays. Yeah. Whatever that means. So using our traffic analogy again, our gamma rays are the motorcycle or the motorbike of radioactivity. Lowest ionizing power, if you had the option of getting hit by a sedan or a motorcycle, and it was like just you, not like in a vehicle or anything, I think we would hopefully all take the motorcycle. Again, a weird choice to make, but if we were in that situation, I'd rather get hit by a motorcycle. It's the lowest ionizing power, but also the highest penetrating power. Weaves through all traffic. depending on how brave the rider is, of course. It's not terribly uncommon. You'll just be driving in normal traffic. You might even be going regular speed. All the lanes are filled, and there goes a motorcycle, right? They don't need any sort of special circumstances. They'll just go ahead and get ahead. And to correlate that penetrating power with real world examples, several inches of lead shielding, so just like bricks of lead, or thick slabs of concrete, like probably a foot or more of concrete. Question?
Is this what's used in X-rays?
No, X-rays are used in X-rays.
Thanks.
Yeah. Gamma rays are emitted by, they're just like out as part of cosmic radiation, and our atmosphere blocks a lot of the cosmic radiation. So part of the reason that we can't easily build on like Mars or other planets that don't have atmospheres is gamma rays, because we would just get fried. You'd have to be protected at all times with like special suits, on top of not being able to breathe.
So you don't turn into the Hulk.
Yeah, so you don't turn into the Hulk or just die. I have done some work with gamma ray emitting isotopes, and so like we worked in a special fume hood that had lead lined glass, which is like yellowish in color, and we had all these like, we literally had like lead bricks, and you would build up a little wall of lead bricks, and then you'd work behind that, looking through the lead glass. So that was kind of cool. The reason that we had to work in a fume hood is because it was volatile, and so if you worked with it outside of the fume hood, then it might just get all over you, and then you'd have to like, if you got it on your clothes, then you'd just say goodbye clothes for 238 days or 300 days or whatever. We'll get to that in the half-life section of things, not the video game, by the way. Okay, positron emission. This is our number 4 for radioactivity. The positron is the antiparticle of the electron. You don't really need to know what all of that entails, but one way that we can see that show up is it's got a positive charge instead of a negative charge. The electron also used to be called the negatron, or a negatron, I think, and so negatron and positron works really well together. I don't know why we changed to electron, but we did.
Sounds too similar to Transformers.
It does sound transformer-y. So the positron, being the antiparticle, it's like dark electron. It's got the same mass, but it's just the opposite charge, and so it has a positive 1 charge instead of a negative 1 charge. If a positron and an electron meet, they annihilate each other. They just blow up into gamma rays. In positron emission, a proton is converted into a neutron as it emits a positron. So it's sort of the opposite of beta decay. Also relatively easy math, arguably easier math because we don't have a negative number to deal with. So the net result of positron emission is that a proton turns into a neutron. So you'll move 1 step down on the periodic table, but the mass number stays the same. They're about equivalent to beta particles in terms of ionizing and penetrating power. Not dark sedan in the spirit of like Dark Brandon or Shadow Fighters in like Smash Bros. They're the evil version of an electron, if you want to think of it that way. Okay, write a nuclear equation for the positron emission of sodium-22. I will let you do the whole thing this time while I play my memory game. All right, nuclear equation, here we come. Sodium-22, the 22 is the mass number. That's the upper number, it's the bigger number. Sodium has the symbol Na. And it's got an atomic number of 11. That's from the periodic table. It is positron emission, so we're losing something, and it's going to turn into something else. So our parent nuclide here is the sodium-22. Our daughter nuclide is, we'll find out. And we need to bring to the table positron emission. It's 0 over plus 1 e, the opposite of our beta particle. And so our equation for this, for the top, surprisingly, 22 equals 22 plus 0. And on the bottom, 11 equals something plus 1. That something must be 10. And then we would find 10 on our periodic table, neon. So that would be our nuclear equation for positron emission. Questions? Here's a table that's a nice summary. This is from our online book. A nice little summary of our types of decay. There's actually a secret fifth type of decay that I didn't include because I don't care about it. Also, I haven't taught it in the past, so nobody said anything, so I'm sure it's fine. I don't remember. You can go to the book to find out. All right, where radioactivity shows up is everywhere, as it turns out. Radioactive stuff is all around us. Naturally radioactive elements either have a very long half-life, causing them to still be around, or they are continually being formed by some other process. The reason that naturally occurring radioactive isotopes have long half-lives or are being formed constantly is because they had short half-lives. We wouldn't have them anymore. They would already have moved on to smaller, better things, perhaps. Uranium is our heaviest naturally occurring element. If you look at the periodic table in the class, it's the last one that's a filled-in symbol. Everything that's a higher atomic number has that empty symbol. That means that it's only available if it's produced synthetically. So somebody has to make it in a lab using some of the stuff that we're doing here. That decays to thorium-234 with a half-life of 4.47 billion years, which means that after a period of time, if you have some sample of uranium-238, if you wait 4.47 billion years, now you only have half of the amount of uranium-238 that you started with. And the other half would have turned into thorium-234. Thorium-234 is also radioactive, and that decays to this other thing, and that has a half-life of 24.1 days. So that's not around for very long, relatively speaking.
What's the half-life of thorium?
That's the
20?
This particular isotope has a half-life of 24.1 days. So after less than a month, whatever amount of thorium-234 you had, half of it's gone. And these half-lives only apply to these specific mass number versions. So like there could be a uranium-236 that has a half-life of like 5 seconds.
So every 24 days it gets cut in half?
Yeah, it gets cut in half every 24 days. This is an example of what one such natural decay series might look like. So there's a bunch of different jumps that are going on here. Anytime we're dropping down one spot, that's an alpha decay. Then we can jump up and to the right with a beta decay, and it looks like we don't have positron decay or positron emission. So there's a bunch of different ways that these things can break down. Initially, we started with U-238. It goes through a whole bunch of things, and then polonium, further down, 218, can either go through beta decay or alpha decay, and then those get to bismuth, and there's a whole wiggly web of decay. The end result here, though, is lead. All roads lead to lead. Lead to lead. So all of the U-238 that's existing and all of the other things that are in this big web of decay series, they all end up turning into lead-206. At the same time, though, all of these other things exist, even though some of them have very short half-lives, like this polonium-214 has a half-life of 164 microseconds. So that's gone, like instantly, compared to like 22 years or 5 days or even 4 minutes. Radioactivity is a natural component in the environment. If you take biology classes, you'll probably learn about some of the mechanisms that we have, that our bodies have developed to fight against radioactivity. We wouldn't be here if we couldn't withstand a little bit of radioactivity. There are small amounts that make it through the atmosphere, which is not great for us. Some of that also gets caught in the upper atmosphere and produces different isotopes, like of carbon, get produced up in the upper atmosphere, and they make their way down here, and then we eat them. The ground also contains radioactive atoms. I believe we do have a little bit of uranium, like if you drink well water. There's probably a little bit of uranium in your well water. Not enough that you could do anything with it, but it's there. It's probably not harmful. Anything that's beyond bismuth, you can find bismuth, it's one more than lead. Those are all unstable and radioactive. And there's also some radioactive elements that have less than 83 protons, so smaller things. So the half-life we've been talking about, what is it? What does it mean? So the nuclides decay at different rates. These rates are independent of outside factors. You probably don't remember, but way, way back in the beginning of class, like the second lecture maybe, we talked about the second. The second, our period of time, is based on a particular nuclide and its decay rate. Because it doesn't matter what environment it's in, it doesn't matter what the temperature is, there's not any of these outside factors that influence its decay rate, and so it's a reliable way of counting time. Just, however many billions of little emission events you detect. Okay, well, you hit your target, that's 1 second. Half-life is the time it takes for half of the parent nuclide to decay. our amount gets cut in half. If you go through one half-life, your number gets cut in half. Let's say that we have 24 radioactive boxes. Why they're radioactive, I don't know. We bought them at the radioactivity store. After one half-life, usually given that symbol T sub 1/2, T for time, half for half, we would have 12 boxes. If we went through another half-life, that cuts the number of boxes in half again. We now have 6 boxes, 6 radioactive boxes, not 0 boxes. So one common misconception is addressed in this first big red bullet point. It does not decay to 0 atoms in 2 half-lives. It gets cut in half, and then it gets cut in half again. And then it gets cut in half, and then it gets cut in half, and then it gets cut in half, and then it gets cut in half. Just continually until you run out of things to cut in half, and then your one just disappears. You can calculate in between half-lives, so like a quarter of a half-life occurs, how much you have left, but you need to use natural log and some equations to do that, so we're not doing that. Isn't that nice?
Yes.
So we're only working in full half-lives, and like if it's between half-lives, just like, well, it's between this amount and this other amount. We're not getting into the messy ln stuff. Nuclide, or a radioactive isotope that has a short half-life, is very active, lots of decay events. It decays very quickly. It emits a lot of radiation. Radon-220 has a half-life of approximately 1 minute. That's a lot of decay events. So if you have a significant size sample, like you can see it with your eyes sample of radon-220 for some reason, that would be a very bad place to be. Unless it's behind lead bricks, lead glass, large slabs of concrete, because if you're close to it, you're going to be hit with a lot of radioactivity. Versus uranium-238, that's the one with like the 4 billion year half-life. If you had the same amount of atoms, it's not going through that many decay events. That's why it's around for so long. So it probably wouldn't be that bad to be around compared to this radon-220. Thorium-232 is also much less active with a half-life of 14 billion years. Also much less active, fewer decay events, safer to be around.
Is there a specific radiation that was left in Chernobyl?
I don't know what the amounts of radiation in Chernobyl are. I'm sure you can find it online though.
No, I was asking like a specific type of radiation, or if it's like all.
I think it's alpha and gamma. Here's a graph of half-life. So on the x-axis, we have time represented in half-lives. So 1 half-life, 2 half-lives, 3 half-lives, et cetera. On the y-axis, we've got the percent of material remaining. So starting with all of our material, after 1 half-life, our amount has been cut down to 50%. After 2, it's cut down to about 25. And then you cut that in half, 12.5, 6.25, 3.165, you know, whatever.
Cesium and iodine.
Again, these half-lives are unique and not affected by physical conditions or chemical environment. You also, for this class, don't need to memorize any of the half-lives. We can do questions with half-lives. So let's say we have a plutonium-243 sample it initially contains 0.256 moles. We want to know how much is left after 30 hours. And we're given, because we don't have to memorize it, the half-life is 5 hours. There's several ways to do this. I've come up with equations for how to do it in the past. I never remember them because I don't use them. But if you really need an equation, I can try to come up with something for you, or you can look it up. All right, we've got 30 hours as our time point that we're looking at here. I'm going to switch that to green. We've got 30 hours. We've got a half-life time of 5 hours. What can we do with that? Any ideas? If we've got 30 hours that pass and 5 hours per half-life, we can calculate the number of half-lives that pass. And what does a half-life do to the amount of material that we have? Cuts it in half. So there's one way that we can do this. We can start with our 0.256 moles. That's not a 6. That's a 6. We need to cut it in half how many times? 6 times. So we can multiply by 1 over 2. 6 times. And that'll get us the correct answer. You could also put into your calculator divide by 2 raised to the 6th power. That's the same. You could do these divided by 2's individual times. You could do 2 times 2 6 times. That's the 2 to the 6th part. And then just divide by that. Whichever of these methods you feel works best for you, they'll all get you the same answer. Let me pull out my calculator. .256 divided by 2 raised to the 6th power. 0.004 moles would be left. And we could add zeros after that if we cared about significant figures. So for example, if you wanted to do it one at a time, you could just write out, I divided it by 2 once, 0.128. I did it again, 0.064. I did it again. You would want to keep track if it's 6 half-lives, just in case you lose track. Because there would probably be a 0.002 and a 0.008. That would be other options. Questions about that? ways that we detect radioactivity include a Geiger or Geiger-Müller counter. So the way that these work is you hold a little box. It's usually got a little wand attached to it. The box has a bunch of settings on it. And you just point the wand at things, and it says if it's detecting radioactivity or not. And it'll usually have, in this case, it's got a counter. A lot of the time, it'll just have like a dial, and you can set the sensitivity, and then the dial will move around depending. Or it'll have a little counter like this, and it'll also usually have a little click setting, so you can have it make that classic clicking sound, like if you've played Fallout, that clicking sound. That's what's going on here. So the lab that I worked in where we were doing the radioactivity stuff, I got to check myself with one of these every time I was done doing an experiment to make sure I didn't have anything on my shoes. The half-life of the thing that we were working with was 30 days. And the rule of thumb is that after 10 half-lives, it's basically all gone. So I would have had to have, if I had radioactivity on my shoes, I would just take my shoes off and I would leave them in the lab for 300 days and then come back and get my shoes. Otherwise, if I have radioactivity on my shoes and I don't detect it and I'm walking around in the hallway, now I'm leaving a nice trail of radioactivity that's exposing everyone to radioactivity.
So was there just a closet full of a bunch of shoes at this lab?
I think people were just really careful and they didn't get radioactive stuff on them. It did happen occasionally, like you get it on your clothes and then goodbye clothes, you know, see you later.
Did you guys just keep an extra set, like just in case?
I didn't keep an extra set, no. So if I had spilled on my pants, that would have just been awkward. Taking the company bus back to my house. A way that radioactivity is often used is for radiocarbon dating or carbon dating. As you may have heard it called. And I talked a little bit about this, about some of the stuff that goes on with this before. So radiocarbon dating uses the presence of carbon-14 in the environment. And the amount that you detect and the amount that's like out in the environment, you can compare those two numbers and see how long it's been since this thing had new carbon in it. I think it talks about that more here. So carbon-14 is constantly formed in the upper atmosphere. We get neutron bombardment of nitrogen. Those neutrons hit nitrogen and turn into hydrogen and carbon-14. Carbon-14 is radioactive. It's got a half-life of 5,730 years. And that carbon might be present in CO2, for example. And since it's constantly being formed and decaying, it's been a long time, we basically have a constant amount of carbon-14 in the atmosphere. It's gone up and down a little bit, but that gets turned into carbon dioxide. Plants turn that carbon dioxide via photosynthesis into food that can make its way into our bodies or into the bodies of animals. And then, since you're consuming stuff that's got carbon in it all the time, you should expect to have about the same ratio of carbon-14 to carbon-12 as whatever's out in the atmosphere. And then when you die, what happens? You stop eating. And since you stop eating, you stop incorporating new carbon-14. When you die, you stop eating. And so your carbon-14 decays. No new carbon-14 added. Right? You can't eat more stuff that has carbon-14 in it, and so the amount of carbon-14 in dead things slowly over time goes down. And so you can compare with half-life and knowing about how much is in the atmosphere, you can compare those amounts and figure out approximately how long it's been, using some of that math that we're not doing in this class. The maximum age that you can effectively use with carbon dating is about 50,000 years, because that's about 10 half-lives. Once you get past 10 half-lives, if you cut something in half 10 times, you've cut it down to a really, really small fraction, and so you'd have to have really high precision instrumentation to be able to measure that. Another thing is that you can check against things like counting tree rings in old trees, or like taking ice core samples. Since there's going to be trapped carbon dioxide in those samples, you can check it against those. Oh, it's 5,000 layers under, and so that's however many seasons, what have you. And there's a little bit of plus or minus, maybe 5%. But it's a cool way of being able to check the age of things. Let's say an artifact peddler, someone who peddles in artifacts, not like on a bike, but selling, claims to have a partially fossilized grave marker from a peat bog in modern Denmark. The marker is inscribed with runes consistent with the writing from the 700s CE, so like 1,300 years ago. A measure of its carbon-14 content reveals it to contain 100% of that found in living organisms. Is the grave marker authentic? Carbon-14 has a half-life of 5,730 years.
No.
We've got a guess for no. We've got a couple guesses for no. Why not?
Because it has the same amount of carbon found in living organisms.
Yeah, it has the same amount of carbon found in living organisms. That means it must have been alive recently. After 1,300 years, a measurable decay, or a measurable decrease in carbon-14, we'll write it the other way, would have occurred. So we would expect to see something less than 100%, something more than 50% compared to living organisms. We don't do that ln math in this class, and so we wouldn't know the exact amount, but that's why it could not be legit. That's pretty much all of the important stuff. For this chapter, the rest is just like nukes and fission and stuff. So we'll talk about that on Thursday.